Awesome. Okay, so it's about 11:02 here. So I'll kind of go ahead and get started. So I'll let people kind of continue filtering in as we start. But yeah, welcome everyone to the Neptune Triton System Seminar Series. These occur every month on the second Tuesday at 11 a.m. Eastern. I apologize for the confusion around GMT. I was notified early this morning that may have been a little confusing for some people because of daylight savings. So I apologize. So going forward, rather than kind of going on GMT or UTC time, we're going to keep to 11 a.m. ET time, Eastern time. So today's speaker is going to be Dr. Ravit Helled, and so I'm just going to actually stop my screen share right now, and if I can figure out how to do that, yes, okay. And so I'm going to kind of let Dr. Ravit Helled sort of take the screen sharing, and while she's doing that, I'll sort of introduce her a bit. Let's see here.
Okay, can you see my screen?
Yes, we can.
Wait. Okay, one second.
Sure.
Okay.
Sure.
No,
sure.
now it's okay. I think now it's okay. Can you see it?
We
No?
cannot. Yeah, maybe retry sharing.
Okay, 1 second.
Sure.
Maybe just the movies that will not work, so it's okay.
Yeah, we see that.
Okay, can you see
yes.
now?
Yeah, that's okay. Perfect. That's perfect. Yeah. Okay, so Dr. Ravit Helled received her PhD in giant planet formation from Tel Aviv University, and then spent some time at the University of California, Los Angeles as a postdoc and a research fellow. She returned to her alma mater at Tel Aviv University as an associate professor before becoming a professor at the University of Zurich, where she has been since 2016. Dr. Helled is a member of Juno's science team and is one of the lead scientists on ESA's JUICE mission to Jupiter. Her research has included the formation, internal structure, and composition of the outer planets, and how these might compare to the evolution of exoplanets. She was selected as one of the 50 most influential women of Forbes Israel in 2015, and in 2010, she was involved in the effort to accurately calculate the rotation period of Saturn. So today she'll be talking about the origin, evolution, and structure of Uranus and Neptune. So thank you so much for joining us today, Dr. Helled, and feel free to take it away.
Okay, thanks, Jody. So can you hear me okay?
Yes, we can hear you.
Okay, great. So I know this is really focused on Neptune, but I think I will also mention Uranus, because there are some differences between Uranus and Neptune that I think are important to identify. And a lot of what I'm going to tell you today, you can read in more details in two recent reviews. One is Helled et al. And one is Helled and Fortney, that were focused on the internal structure, formation, and evolution of Uranus and Neptune. Okay, so there are really fundamental questions that remain unanswered when it comes to Uranus and Neptune. First of all, we don't know how they formed and how they evolved with time. We are still not sure what they're made of. Often we say Uranus and Neptune at the same breath, right? We think they're like very similar planets, but they could be different. And the question is how different they are. And if they are really different, in what? And what is the reason for these differences? Another important thing to note as for planetary scientists is that Uranus and Neptune really represent a unique class of planets. They are very different from terrestrial planets that are dominated by refractory materials, and they're also very different from planets like Jupiter and Saturn that are hydrogen helium dominated. They are dominated by heavy elements, but not refractories, and we don't have a very good understanding how to model them. So they are very challenging in this perspective. Okay, a bit of basic facts about the planet. So here I show you the masses of Uranus and Neptune. You can see that Uranus is a bit smaller than Neptune. Both are located at the outer part of the solar system, so 20 and 30 astronomical units. These are their 1 bar temperatures, so they are cold. We think that the atmospheric composition, that the helium there is in the protosolar ratio, but actually the atmospheric composition of both planets is very uncertain. We don't know whether they are water-rich planets, are they really failed giant planets, and where did they form? That's also a key question. So we see them today where they are at 20 and 30 astronomical units, but we don't know whether this is their original formation location. It is really important to constrain their composition, because then we can better understand, the formation of our planetary system, so the formation of the solar system. And again, that can also give us some clues about the formation location and their formation timescale. So here I show you some sketches of the internal structures of Uranus and Neptune. I will come back to that. Okay, I also mentioned that these two planets are different. So they have similarities in terms of mass, sizes, rotation rates, we think, and also their location in the solar system. So both are far away from the sun, although they still have 10 astronomical units difference. But they also have clear differences in the physical properties, like the flux, the tilt, the atmospheric composition, we think. The atmosphere dynamics, the activities, just by looking at these two images, you can see that Neptune seems to be more dynamically active than Uranus. And they're also very different in terms of their satellite system. When we make models, what we do is basically we use the available observations. So we take the observational constraints and then we try to make a model. So what are the fundamental observations? So these are the masses, the sizes, the angular velocity, so the rotation rate of the planets. And then what we really need for structure modeling are the gravitational moments, or the gravity field. So for Uranus Neptune, we only have J2 and J4, and these are from Voyager flybys. We typically want to have the 1 bar temperature, so we can start our structure models from there. If we have atmospheric composition, that's an additional constraint we can use for the models. So these are the standards, but of course, in principle, the more measurements we have, the better, because that helps us to constrain the model. So, for example, the shape of the planet, so not just mean radius, but the actual shape, the moment of inertia, the magnetic field, dynamics, and heat transport mechanisms, and all these things can be applied. But I should say that shape and moment of inertia and magnetic fields are something that we can measure, and then we use that to project on the internal dynamics and heat transport mechanism. These are not measurable. So basically, maybe the main message from this slide is that we need a mission, because actually the uncertainties on these properties for both Uranus and Neptune are very large. So they're very uncertain. We have large error bars, and that means that we have a large parameter space for solutions. So of course, if we have more accurate measurements, we can pin down the structure better. So as I said, how well do we know those? Well, not very well. Okay, when we make a structure model, so of course we have to start with some assumptions, and the assumptions are that the planets are spherically symmetric or oblate. We also assume that they are in hydrostatic equilibrium. And then we have to, basically we try to find the interior parameters. So we basically constrain the density, pressure, and temperature profiles. And we we solve the basic planetary equations, so the mass conservation, hydrostatic equilibrium. We have to assume something for the temperature profile, so the way that heat is being transported, energy conservation, and the equation of state. So that's to basically represent the materials that these planets are made of. But as I mentioned, for both Uranus and Neptune, we have only J2 and J4 measured, and they are measured with rather large uncertainties. And that means that we have a large range of possible internal structures. So we actually cannot, constrain the composition and how it is distributed within the planet very well. At the same time, I should also be fair and say that the gravity data are typically insufficient to constrain the composition and internal structure directly. Again, this is something that has to be inferred indirectly, but the better the measurements are, the more we can constrain the structure. And when I mentioned at the beginning that both Uranus and Neptune represent a unique planetary group, it also means that we actually don't know what is the best modeling approach for those. So should we assume, for example, these planets are water rich and have these 3 traditional layers? Are they more silicate rich? And again, should we model them with this type of traditional 3 layers? There is now some activity regarding the potential silicate rich nature of the planets. And it's possible that they don't have distinct layers, which is now something we see for both Jupiter and Saturn, and that might also be true for Uranus Neptune. And personally, I think that that's probably the right way to model them. Now I just want to come back to the point about the fact that we always think that Uranus and Neptune are water rich. And typically the reasons for that, or at least I could come up with 2 good reasons at the time when I thought about that. And the first one was that they have magnetic fields. Both have quite strong magnetic fields. And in order to generate a magnetic field, you need to have, besides some rotation and convection, you need to have the material being electrically conductive to generate a dynamo. So in principle, that gives some constraints on the composition. And indeed, it was suggested that if you put water at high pressures and temperatures, you can get ionic water or superionic water. And this material is electrically conducting, and that would explain the magnetic field. And this is a reason to support that maybe these planets are water rich. And then the other answer is that, since they are far away in the solar system, they are far from the sun. And if you think about the solar nebula, the temperatures were low enough there to have condensation of water ice. And of course, oxygen is very common. So we would expect the building blocks of these planets to be water rich. But now we can question that, and I come back to the magnetic fields and I ask, is it really that it's only water that can expand the generation of the magnetic field? Could it be that there are other materials at high enough pressures and temperatures, maybe even silicates with a mixture of hydrogen, that could lead to magnetic field generation? So actually this argument of magnetic fields is not that strong, or at least not as strong as you guys may think. Okay, then what about water being so common in large radial distances? Well, we have Pluto. And now we know pretty well that Pluto is actually rock dominated. It has 70% rock and only 30% water. So why would Uranus and Neptune be different? So it's actually possible that both of those planets are not water dominated. And this is why I personally don't like too much the name of the icy planets, because I think that it gives us the wrong impression that they are made of or dominated in terms of composition with water ice. Of course, when we say ice, we also mean ammonia ice and methane ice for these planets, but they could actually be more dominated in terms of composition by other elements like reflector materials, like silicates, for example. But we don't know. And this is just an example that's already pretty old. But in this paper, we basically wanted to make the point that we can satisfy all the observational constraints also when we make models that have no water at all. So I don't say that Uranus and Neptune have no water. I just say that according to the data we have, there is no direct evidence that these planets are water dominated. So here you can see the differences between models that have water and hydrogen and helium and another model that has only SiO2 and hydrogen and helium. And you can see the density pressure profiles. And basically, as I said, both of these extreme models can explain all the observational constraints. So this is something we have to keep in mind and ask ourselves, how well do we know these planets? And maybe we should put away some misconceptions that we have about the planet. And again, I have to remind you that the gravity data is insufficient to constrain the planetary composition and also to identify density jumps. And in this paper, we also showed that in principle, both planets could have a density profile that is continuous. So you don't necessarily have these, distinct layers or core envelope boundaries and things like that. It can be that the density is much more continuous than we have in, for example, terrestrial planets. Okay, so we said that. So the gravity data can give us some constraints on the density profile of the planets. For Uranus and Neptune, we have only J2 and J4 with large uncertainty. We want also to go to high order harmonics. but we have to keep in mind that these higher order harmonics provide information on the outer regions of the planets. On the other hand, if we constrain this region, it also reflects on the deep interior. But in any case, this topic of structure models is degenerate in the sense that the internal structure and chemical composition are always inferred indirectly from the model. And this is also means that they depend on the model assumption. So this is something we cannot fix because we will always have this problem. But as I said, as we have better data, we can exclude certain solutions, and this is how we can make progress. Okay, this is just to show you how it is done. So basically, when we measure the gravity field, so the J's, this can be used to constrain the density distribution in the planet. Okay, so internal structure. So again, the basic idea is that we use the observations as constraints, and when we have more accurate measurements, we have less freedom in modeling. Traditional models of Uranus and Neptune typically looked like that. So they had these three distinct layers. So they had a central core of silicates most of the time, then an inner envelope of ices. So here ices, again, are water ice, but also ammonia and methane ice in smaller proportion. And then an outer envelope, or if you wish, the atmosphere, which is hydrogen helium dominated, but also is relatively metal rich. So it means that it is enriched with heavy elements. And the question is, where is it coming from? Why do we model, or why did people model these planets in this way in the last few decades? So if you actually look back at the literature, you realize that there are not the best reasons, and that might not be the right approach. And we have to keep in mind that maybe the planets look very different from this, distinct layers. So here I show you these distinct layers, and this is basically assuming that everything is separated. So the ices and rocks are separated, and then we have some kind of a phase boundary for with the atmosphere. But it's also possible that ices and rocks are mixed in the deep interior, and you have this kind of composition gradients. Actually, now we know from equation of state calculations that ices and rocks, they like to be mixed together. And it's possible that these are mixed, but still you have some kind of a boundary with the atmosphere. It is possible that the ices and the rocks are separated, but you have a gradual transition here because actually water would also like to be mixed in the hydrogen envelope. And of course, it can be that we have everything mixed. So we have the ices and rocks being mixed because, as I said, we think that this is what happens at these high pressures and temperatures. And again, also in the atmosphere, there is no reason to assume that we will not have more heavy elements here and not have necessarily a distinct layer. So we will not have this, separation between the atmosphere and the deep interior. And as I mentioned, now for the gas giant planets, we clearly see that this is not the case. And here you can look at some papers. And this is, by the way, also consistent with recent models of giant planet formation. So we recognize that formation models actually predict much more of a gradual interior than something that is separated like that. Okay, and again, I would like to emphasize the point that Uranus and Neptune are really unique planets. They are different from the terrestrial planets and the gas giant planets, and we really need a better modeling approach, and we also need to understand better the behavior of material at these planetary conditions, because often it goes to terrestrial planets, pressure temperature regimes, or the ones for the gas giant planets, but not so much for those planets, and not so much for mixtures of things that are not hydrogen helium. And this is very important because it can guide us in choosing, the best modeling approach. So that's something that I would like to see in the near future. Okay, so then the other point is the magnetic field. So I said that both planets have magnetic fields, but unlike the magnetic fields of, let's say, Saturn or even Jupiter, they have really complex multipolar magnetic fields. We think that the magnetic fields are not generated in the deep interior or in the cores of the planets, but higher up. And indeed, models show that if the magnetic field is generated higher up, it will be will have a nature of a multipolar magnetic field. Again, people interpret that as having the magnetic field generated in a region of water at high pressure, so superionic water. But as I said, this could also be generated by another material. This is important to add the constraints for the magnetic field because, as I said, since we know what are the conditions to generate a dynamo, it can tell us that in this region where the magnetic field is generated, we need to have heat being transported by convection, and also we need material that is electrically conducting. So this is where we really want to have constraints from the magnetic field, but also from the gravity field. Okay, then there is also the issue about of the shape and rotation of the planets. In fact, we don't know the deep rotation of both Uranus and Neptune. And this is important because this rotation, as I mentioned before, actually enters into the structure model. So if we don't know the rotation rate of this planet, it also means that it affects the inferred composition and internal structure. And for Uranus Neptune, we had the estimates for the rotation rate from the Voyager flyby using magnetic field data and also from kilometric radio emission. But now from Saturn, we know that this might not represent the rotation rate of the deep interior. And also I should say that for the magnetic field, it's not that Voyager stayed in each planet for the rotation period. So this was something that is inferred. And again, the question is, does it represent the rotation of the deep interior? And it's possible that both Uranus and Neptune cannot be represented by uniform rotation. It's possible that they have much deeper winds. Although I have to say that there have been a few studies trying to constrain the depth of the winds. And according to the gravity data we have today, the winds don't seem to be very deep. But we still don't know what is the underlying uniform rotation. So this is important because also the wind velocities are always given relative to the uniform rotation. So if we don't have a good determination of the rotation period of this planet, it also means that the wind velocities would shift because the zero would be different. So this is also a very fundamental property of the planets that actually is not well constrained. And just to demonstrate why it is important, so again, this is already from nearly a decade ago, but in this study, we modeled the internal structure of Uranus and Neptune, and we just used different rotation periods and shapes. And we wanted to see how things change. So here you can see the outer envelope metallicity versus the inner envelope metallicity for Uranus and Neptune. This is for the Voyager rotation period. You can see that these are the solutions for Neptune. It's a relatively large range of solutions. You see the metallicity goes from 0 to 50%. This is just because the gravity data are very bad. And for Uranus, it's better. So you see a small parameter space of solutions. Okay, so that's with the Voyager rotation period. What you can see here is that basically the solution for Uranus overlaps with the solution of Neptune. So basically they are consistent. They could be consistent. But when we change to a different rotation rate that basically minimizes the dynamical height, and that was published in another paper, in this one in 2010, then we see that the solutions for Neptune shift here, and for Uranus it shifts here. So now they don't overlap anymore. And what it tells you is that it's possible that actually Uranus and Neptune are very different from each other. And this is why I strongly suggest that we shouldn't say Uranus and Neptune together, but it should really be Uranus and Neptune. As I said, they are really unique, and maybe they are not twin planets. And as I mentioned before, maybe we should not call them the ice giants because actually we don't know whether their deep interior is dominated by ices in terms of composition. Okay, so a little bit about the formation of the planets. From the data we have, we estimate the hydrogen helium masses on these planets to be 2 and 3 Earth masses for Uranus and Neptune respectively. So that means a metallicity of about 85%. So again, they are dominated by heavy elements. We don't know what these heavy elements are. But this estimate basically suggested that Uranus and Neptune are some kind of failed giant planet. So that means that they formed a core and they managed to accrete a little bit of hydrogen helium, but somehow they never managed to become gas giant planets. So what does it mean? It means that on one hand, they must form before the gaseous disk dissipates because they do have non-negligible amount of hydrogen helium, but on the other hand, they should not become gas giant planets. So, you need to kind of fine-tune their formation, and this leads to this concept of the fine-tuning problem of the formation of Uranus Neptune, because you want some hydrogen helium, but you don't want to become gas giant planets. And then in the recent years, there have been different papers suggesting how we can explain this formation, because of course you don't want to have such a fine-tuned model. So there is questioning on the in situ formation. Maybe they formed in another location. People looked at the creation of pebbles and planetesimals. There was an idea of collision of embryos. Please look at these papers if you want to get further details. When it comes to giant planet formation, the standard model is the core accretion model. And again, if really Uranus and Neptune are fair giant planets, the idea is that they never reach this phase of becoming a gas giant planets. But let me slow down a little bit here and tell you what we see. So here we see the planetary mass as a function of time. I don't have numbers on purpose because it's very model dependent. Here it's typically in Earth masses. Here it would be about 10 Earth masses, and the time is in a few million years. Okay, and then we have these three phases. So we have the first phase where basically we build up a heavy element core. And this, if you stop the planet here, you will end up with a terrestrial planet. Then there is a second phase where basically there is accretion of hydrogen and helium. So hydrogen and helium is here. Here you have Z in the envelope. This is pure heavy element core. So if you reach this stage, you would have something that looks like Neptune or mini Neptunes. So you would have a heavy element core surrounded by a hydrogen helium envelope. And if you manage to grow even further, you can have the mass of the heavy elements being comparable to the mass of hydrogen helium, and then you reach a stage which we call the runaway gas accretion, and then you end up forming a giant planet. So the idea is that Uranus and Neptune formed during this phase, so they never reached this phase. But of course, you need to explain their exact masses and composition. So that's not so easy. So in the most fundamental model for giant planet formation from Pollack 96, they try to look at the formation of Uranus and Neptune, not even, because it was basically impossible. So they still use a lot of they use the model with many heavy elements to make the growth more efficient. And still the formation timescale was very long. So here you can see it's 20 million years, which is by far much older than, much longer than what we think are the typical disk lifetimes. So this is where, this model fails. But there are a few things to note here. First of all, the formation timescale is long. Here it's a bit shorter when they assumed smaller planetesimals to accelerate the formation process. But another thing that even when they do that, the core mass is around 10 Earth masses, or a bit more. But they don't get the correct final masses, because when it's here, it will actually go runaway. And if it's here, it will have only 11 Earth masses, but we said we need a bit more because it's 2 and 3 Earth masses. And again, this demonstrates this issue of fine tuning. So as I said, there are different solutions to explain to expand the formation. And maybe what we should ask ourselves, if we are aiming at having a mission, is whether there are possible observations we can use to discriminate among different formation scenarios. Okay, I will just do that very quickly. This is a similar plot to what I showed you before about the formation. You have the mass of heavy elements, hydrogen, helium mass, and the total planetary mass. This is the mass of Uranus, and this is of Neptune, and this is the range of estimated hydrogen and helium. So when you make a model, you try to fit the final mass, but also have the right hydrogen helium mass, and you can see that it's not very easy. So basically, again, that's why we have this challenge in explaining the formation of these planets. And another thing is that we have to keep in mind that we shouldn't look at planet formation alone. But we also have to look at the aspect of formation and evolution, because structure, evolution, and formation, because all these three aspects are linked. So because the planet formation would determine the primordial internal structure and how the planet evolves, and the evolution will determine the final internal structure of the planet. So basically, we have to combine those three aspects. Okay, I'm running out of time a little bit, but okay, 5 more minutes, I'll try. Okay, so another thing is that it's possible that Uranus and Neptune actually were formed in a similar way and were more similar to each other right after their formation. And maybe the reasons they are different is because of the evolution, again, because as you can see, the evolution can also affect the final structure. So what we suggested is that it's possible that the differences between the two planets are linked to giant impacts. And as I mentioned before, although the Uranus and Neptune are similar in masses, they are different in terms of their tilt, the satellite system, in the observed heat flux, and also the inferred moment of inertia. So what we suggested is that maybe both planets suffered from collisions shortly after their formation, while for Uranus it was an oblique collision that basically led to the tilt and also to the formation of the satellite, but didn't touch too much the deep interior, so it stayed a bit more layered, while for Neptune it was a head-on radial collision, and that could penetrate to the deeper interior and maybe led to some mixing, and that could explain why Neptune emits more than Uranus. Okay, so these are the movies. So here you can see it's the same simulations of giant impact, just with the geometry of the impact being different. And we see really that the mixing of the deep interior is different. But I'll move on to this slide that basically summarizes it. Whoops. So here you can see a head-on collision, which what we think maybe happened to Neptune, while here we have a grazing collision. So we suggest that maybe this is the reason they are so different. Okay, just I want to mention that after all. Okay, then I showed you that just before, and I hope I convinced you that it's not so easy to find a formation model that basically can explain both the final mass of the planets and the composition, so the right ratio between hydrogen and heavy element. And in a recent study that was led by my student Claudio Valletta, he finds that for a model when you account for the growth of the planet with stable accretion, typically we are missing some heavy element mass. So here you can see some examples for Uranus Neptune. So you can see here Neptune is missing 1.3 or 2.6 Earth masses of heavy elements. For Uranus here, we miss around 1 Earth mass and 2.4 Earth masses. So this is because we get the right hydrogen helium mass, but you see the total mass and the mass of heavy elements is a bit below. And the interesting thing about it, of course, we can find a few models that fit exactly, but they are not very common. So statistically, it doesn't seem very, it's possible, but it's not. I don't feel very comfortable with that. But in many times, we get this missing heavy element mass, and the reason I like it is because it might be linked to this giant impact. So it can be that these are the masses of impactors that are missing to explain this heavy element mass. So this is something we were working on, and the paper has been resubmitted now, and I hope it's going to be published early next year. Okay, so I'll summarize here. So, okay, summary and future research. Okay, maybe the most important thing I would like to convey today is that we have to stick to facts and realize what are opinions or traditions or concepts that might not be linked to facts or actual observations. And we have to ask ourselves, what do we really know about Uranus, Neptune as planets? We still have questions regarding the formation of the planets. What are the composition and internal structures? So not just the bulk composition, but also how the composition is distributed within the planet. What is the importance of giant impacts on this planet? We think that giant impacts are needed to explain Uranus' satellite system. Maybe it's less important for Neptune, but this is something that I think we will figure out in the upcoming years. And as I said, we have to connect structure models with planetary formation and evolution models, because that's the only way we can get a more comprehensive understanding of these planets. Okay, and maybe before we start the discussion, so definitely we need a space mission. If I'm asked, I would say that we need orbiters and probes to both planets so we can constrain them better. And I'll stop here. Thank you very much.
All right, wonderful. Thank you so much. That was such an excellent talk. Yeah, so as we move into sort of the discussion period here, our hope, the reason that this is a Zoom meeting and not a Zoom webinar is that we're hoping to sort of, make this more of a conversation. So allowing people to unmute themselves or raise their hand or whatever they'd like to do to kind of, keep the conversation going and make it more of a discussion. So feel free to do that. Feel free to raise your hand. Feel free to unmute yourself and ask a question or start a discussion. I did see that there was a question in the chat, so I'll just go ahead and ask that here. But while we're doing that, I want to kind of open the floor for people to feel comfortable, using the raise hand feature, which I think is maybe in the reactions link. Yeah, I think it's in the reactions link on Zoom, or just unmute yourself, or if you're not comfortable, you can post something in the chat. That's also fine. Okay, so this question in the chat is, do the off-center / asymmetric dipole moments of these planets imply that the heat transport and convection in their interiors should also be off-center or asymmetric?
Yeah, so the non-dipole nature of the magnetic field implies that the magnetic field is not generated in the very deep interior. And at the same time, we know that in order to generate a magnetic field, we need also to have convection. So this hints that maybe the outer region of the planets is convective, where the deep interior is not. But it's also possible that the deep interior is convective, but it's just not electrically conducting. So as I said, this is something we don't know for sure. But common knowledge does suggest that the fields are generated off center, and this region should be convective. Whether the deep interior is convective or not, this is still an open question. Recent models suggest that both planets, both Uranus and Neptune, are not fully convective. So that means that heat is not being transported by convection throughout the planets.
Okay, great, thank you. Alrighty, so there's another question here in the chat.
Yeah, I see that.
Yeah. Would you like to read it out loud? Would you like me to?
And I can read it. You said that the actual gravity data are insufficient to constrain the internal structure. Will better gravity data, like general light, be sufficient to solve the present concentration of water? What other measurements would you need? Okay, so yeah, they cannot directly constrain. Yeah, it's just, but the more gravity data we have and the better they are, the more we can constrain the model. Definitely, we want to decrease the uncertainty on the gravity data. If it's possible, we would like to go to higher order harmonics. Then, since it can constrain structure models, we would be able, hopefully, to exclude some solutions, and that could help us with constraining the amount of water in the planets. And what other measurements? Well, if we had, for example, like a probe or something like a Juno MWR that helps to constrain the atmospheric composition, that's an additional constraint, because that will already tell us, again, it doesn't tell you that, it doesn't necessarily represent the bulk composition, but it can be used as an additional constraint. So I would like to have that. So if I can choose, I would say I want gravity field, magnetic field, and atmospheric composition.
Okay, great. Yeah, I think Gordon has their hand raised. So yeah, feel free to unmute. Go ahead, Gordon.
Yeah, this is Gordy Baracker. Yeah, very good talk. One of the many mysteries of Uranus and Neptune is that Uranus and Neptune appear to be enriched in carbon by about a factor of 30 times solar. This comes from measurements of methane. But
Right.
measurements of the D to H ratio, the Herschel measurements measured HD, and it was interpreted that the D to H ratio is only enriched by about a factor of 2 times the protosolar value, or roughly 2 times what's in Jupiter or Saturn. So that seems to be a big contradiction that doesn't make a whole lot of sense. The initial paper talked about possibly the idea of a rock rich rather than ice giant.
Right.
And then,
right.
You mentioned that as one of your possible scenarios too, but there are efforts to try to get new data for the D to H ratio to clear this up. But supposing these values hold, can you actually make an interior model that makes sense, or are these really contradictory?
Yeah, so as you said, this is a puzzling fact, right? So one thing can really be that these are rock-rich interiors, so that would help a little bit. We also have to keep in mind that what we measure in the atmosphere and the interpretation of these measurements, the numbers correspond to an assumption that represents the bulk, right? And it could be, if you ask, I mean, again, if I'm asked, I would say that we have to treat these measurements carefully, because it can be, that they don't represent the bulk composition of the atmosphere even. It could be that they're affected by a recent impact and some kind of recent pollution that could happen. So this is why I think, having more data and more information would help, because we would like, personally, I would like to see whether this is really a robust measurement. Does it really represent the entire atmosphere? Is it time, and how it changes with time and so on? And of course, it would be nice to have a comparative measurement between Uranus and Neptune. So I would say, okay, the short answer is this is indeed puzzling. It's not easy to make models that make sense, also not in terms of the formation to explain those ratios. If I would guess, I would say that they don't represent the bulk, so maybe it's not such a big problem. But I think, it is yet to be answered.
All right, thank you.
Alrighty, yeah, and then I think Heidi Hamel had her hand up, so go ahead, Heidi.
Hi, thanks for that great talk, Ravit. I've commented a question. My comment is, I know I'm biased, but I tend not to think of these as failed giant planets. I think of them more as seriously successful super Earths. So just a little language thing there. My question was about when you were showing this plot of how the rotation period might have implications for the internal structure. I didn't quite understand that. I wonder if you want to take another crack at it that maybe I could grapple with. And then also, how much was the rotation period changing between the two different models that you showed? Thanks.
Okay, so for your first comment, I totally agree. I don't like failed giant planets. I also don't like icy giants, like the ice giants. I really think we need to think about the name. It's not easy, but anyway, point is taken, and I totally agree. Okay, regarding the rotation period. So what happens is that basically, okay, maybe I'll start with the third question, which is easier. So the difference in rotation was pretty large. So for Uranus, Voyager was 16.6, and we suggested 17.24. So slower rotation, and the other way around for Neptune. So instead of Voyager of 17.5, we suggest no, it's the other way around. Yeah, 16.11. So it's really a difference. So basically, it's the opposite direction, and it's nearly 1 hour. So it's a big difference. Is it reasonable or not? Again, this was, I didn't have time to talk about it, but this was based on the minimization of the dynamical heights. And when we do that for Jupiter and Saturn, so when we do it for Jupiter, we do get the right rotation period. And for Saturn, we got this 10 hours 33 that now seems to also be supported by ring measurement, ring seismology measurements, and so on. So if they have a similar nature in terms of the dynamics, this is what we suggest. I don't say that these are the rotation period, but I just actually want to say that we don't know the rotation period because Voyager, was very limited. So we have to reassess that point. What is the real rotation period? I don't know. Okay, so then regarding the middle question. So it's because when you make a structure model, basically what you have is you take the total planetary potential. So you take the gravitational potential, and then you have the J's, and then you have also the centrifugal potential, and that has the rotation period. So then when you build up your model, and then you make the structure model, this is a parameter that directly enters your model. So this is, if you change the rotation period, it also changes your solution, and this is where it is important.
Thank you very much.
All right, and I think there's a question in the chat now. So you seem to have used pure water for your interior models. How well are the EOSs of water and mixtures of water and other volatiles, such as CO2 or NH3, known at the prevailing extreme PT conditions? And how sensitive would your models be toward these uncertainties?
Yeah, so that's a great question. And this is very important. So clearly, as I said, structure models and the inferred composition and internal structure is sensitive to the model assumption and to the used equation of states. And we don't understand the equation of states in a perfect way. And mixtures could be important. And as I said, not so much in terms of, the density, because, actually additive volume law where you have a mixture is not too bad, but it's more, whether you should separate the different compositions and do you have some gradients that could inhibit convection, because that will change the temperature profile, and in return it will change the composition pretty substantially. So the answer is people are working on these calculations, and as I mentioned in my talk, unfortunately Uranus and Neptune really fell in the middle, that they don't have low enough pressure like in Earth, so there is a lot of literature, and we have measurements and data for Earth-like conditions, and there was also a huge amount of progress for Jupiter-like planets, especially for hydrogen helium, and less for this intermediate regime. So it's not very well explored, but people are now waking up, in particular due to exoplanets, that this information is needed. So now people are looking at mixtures better. When it comes to Uranus and Neptune, as it is now, the measurements that we have, in particular the gravity data, are so bad that the equation of state is of a secondary order. Once we have better data, like we have, for example, for Jupiter and Saturn from Juno and Cassini, that will be more and more important. So I hope that in the upcoming years, people will focus on that. And we are working pretty closely with people who do high pressure experiments and calculations, so we can really take this information to our models.
All right, great. Yeah, Leslie Young, go ahead and unmute yourself.
Thank you. Very interesting to think about the formation followed by giant impacts. Can you say something about the timing of the formation, and then do you have giant planet migration in your models before the impacts? Do the details of the giant planet migration have any influence on the results of your models?
Yeah, okay, so there are many different questions in this question, and they are not easy to answer. But okay, so for the formation, I will say that there are some models that include migration and some models that are in situ. In terms of the formation timescale, it typically should be a few million years, with an average of 3 million years, more or less, because this is the average lifetime of protoplanetary disks. Of course, the solar nebula could have a bit longer or shorter or longer timescale, but this should be a few million years. And then we need to have the gas disk dissipating. So that means that whatever interaction, well, if it's gas disk driven migration, it's already before you had the giant impacts, and we got the hydrogen helium mass from the disk. When the giant impacts occur, we don't know. It should be shortly after the formation. Not so much because we can constrain it from the structure point of view, but just because it's also more reasonable to assume that impacts occurred at early times, just because the solar system was much more full with these kind of embryos or objects. It's not very easy to constrain that, and there is always the interplay between formation and evolution, and also structure model that is not very well known. So there is some room to play. So in principle, one could also have models with migration, without migration, later impact, and earlier impacts, but it's hard, right? So it's hard to pin it down. I think shortly after formation makes more sense, just statistically speaking.
Okay, wonderful. Yeah, so if anyone has any other questions, feel free to raise your hands. And if there aren't any more questions, then we can kind of move into sort of community updates. So for this seminar, this is kind of the last few minutes or so of each of these. We're going to sort of do newsworthy items that are relevant to the community. And so before I put this slide up, I'm actually going to open the floor up to Mark, who has his hand raised.
All right. Well, good morning for me. Good afternoon. Thanks, Ravit. A great talk. I actually just wanted to give you an opportunity to talk about the possibility of detecting normal mode oscillations of the giant planets, and like what we've been able to do at Saturn with the rings, and how does that potentially impact our understanding of these interiors?
Okay, so if we can do such a thing, I will be the first to support that. So from what I know, it's going to be pretty hard for Uranus Neptune. But this is critical, right? Because it gives you an independent way to constrain the internal structure. And it has been very successful in the case of Saturn. So I think it is very important. If we can make the case that this is detectable, and we can link it to the deep interior, I think this is a very important measurement we can do. Yeah.
It may not be possible. Thank you.
Yeah, Leslie, go ahead.
People might not know that 44 high quality Uranus light curves have just been submitted to the PDS by Dick French. Of course, useful for the atmosphere, but I'm not sure if the rings can be used for any of this normal mode stuff.
Okay, thanks. That would be really interesting and cool. And I'm really happy to see that people are thinking about this direction, because I think we really need to take different pieces of the puzzles and kind of put them together and get a more coherent understanding. Yeah.
All right, so if there isn't any more discussion, then I'll, just kidding. Yeah, Heidi, go ahead.
I just wanted to mention, for those of you who don't follow astrophysics, that just last week they released the Astro 2020 Decadal Survey, Pathways to Discovery, blah, 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 blah. And one of their top recommendations is a large UV optical infrared space telescope. It's going to be long-term. We're not talking about next year. We're talking about in a decade or two. But this telescope, like Hubble before it, could have great potential for outer planet observations. And so I encourage particularly the younger community members to get involved now on the ground floor, kind of like I did 20 years ago when I was younger with James Webb Space Telescope. It takes a long-term commitment to make sure that these future space telescopes can do the right kind of science to complement the in situ space missions that I totally agree that we absolutely need. But you know, they work together. So I just thought I'd let the community know about that, and to start talking to your grad students and postdocs about getting involved in the large space missions. Thank you. Oh, sorry, wait, ground-based too. That super, they also on the ground, they also proposed, they put support for the 30-meter class telescopes, which would give us Voyager flyby atmospheric quality imaging for Uranus and Neptune anytime we looked at them. Won't give us the gravity measurements that we desperately need for the results of this talk, but still, you know, we take what we can get. All right, now I'll stop talking. Thanks.
Yeah, Leslie, go ahead.
So reacting to Heidi, you know, it might be useful if people like you and John Stansbury and Brian Holler make up a little list of make sure they don't make these mistakes. They always try to make these mistakes, you know, so tracking moving objects is obvious, but also you want to actually be able to observe at opposition and things like that.
Yeah, that's dictated, of course, by the architecture. And that's exactly, Leslie, why we need people working on these missions now during the development phase and not waiting until they're done and saying, oh, but you forgot to include my methane filter. Yeah, it's not, I don't think it's going to be John and I, it's going to be the next generation of young people. So, but yeah, your point's well taken. Exactly.
Right. But you can remind us, okay, so it's a little bit of fighting the last battle, but it seems like some of the skirmishes are frequent, and you can help remind the next generation what to watch out for.
Yeah.
Yeah, Brian, go ahead and unmute yourself.
Hi, can you hear me? In that same vein, the highest ranked Earth-based telescope to come out of the decadal was an ELT. We don't know if it'll be TMT or GMT or some combination or both or what. But second ranked along with CMB-S4 is the ngvla, which is something I work on, which will be fantastic for imaging not only Uranus and Neptune, but basically everything in the solar system. And a number of us have been involved in writing there's a whole science book for the ngvla, and a number of us have been involved in writing chapters on solar system. IMCA was on this. Yeah, IMCA primary authored the main chat. We instead of breaking it up into separate little chapters like a lot of topics did, we put everything in one. So IMCA was deeply involved and first authored that, and we had a radar paper, and there are other things. So anyway, it'll have a lot of applicability, and we don't have to, unlike the UV OIR orbiting telescope, we don't have to wait until 2050 for it to be in flight. Hopefully end of this decade, maybe, fingers crossed. Anyway, something to look forward to.
Yeah, absolutely. Okay, so I'll go ahead in the last couple minutes here, just so people have a chance to sort of get off to their next meetings. I'll kind of quickly flash up some kind of community news relevant to people who attend these seminars. And this is just kind of to make sure that people are staying up to date about stuff, exactly what, Heidi and Leslie and Brian were just bringing up, things that are relevant, to our community. And so there's a couple of things that I just wanted to kind of, flash up here. You can read through them, and I'm also going to post these into the chat so that you can get the links. There's a couple open positions that would be relevant to individuals in this community, as well as a few meetings that let's see that are coming up there. And then I just wanted to say before everyone signs off that the next Neptune Triton System Seminar Series is actually going to be in January. So we're going to be skipping the second Tuesday in December because it overlaps with the AGU meeting. So just so that we don't have to kind of coordinate with that and make sure people don't have, overlapping conflicts or anything like that. We're going to be just skipping it, and then we'll have one starting first thing in January with Dr. Corey Cochran. So, and the link and everything should be in the chat there. And so, with 1 minute left at the hour, I just want to say thank you all so much for joining us today. And feel free to sign up on the mailing list to get more information about these seminars. You can do that at this this Neptune Odyssey jhuapl.edu/events page that's in the chat now. And of course, thank you again to Dr. Ravit Helled for giving an incredible presentation. And I hope you all have an excellent rest of your day. Thank you all so much.
Thank you. Ciao.